So I think that after today's class, we'll be halfway through this semester. And often with really, really big classes that have 900 students like this one or something, they'll assign one course teaching load to only half of the semester. So a lot of the times around this time of the semester, you get a new prof. It might be happening in bio or something. But that's not happening in physics. I got assigned two to teach both halves of this course because I requested that. I like to kind of see things through. I met you guys in September 8th, and I want to see you right through to December. I heard a rumor that the final exam is going to be December 16th, but we'll keep that on the down low. It'll be posted pretty soon. I think it's a Saturday, actually, but that'll be the last you see of me is this final exam. And then in January, you do get a different professor if you're continuing with Physics 132. So today we're finishing off Chapter 6 on momentum. Chapter 7 on Monday is going to start in with energy concepts. But it's a similar sort of concept, is that you can, if there's no external impulse on a system from external forces, then momentum is conserved, and we can use this to solve certain types of problems. And then in Chapter 7, what we're going to learn is that if there's no work done on a system or work done by the system on this environment, then you say that the energy is conserved. And you can use that to solve certain kinds of problems. But why don't we get things rolling with a top hat question? So again, there's a lot of collisions and explosions in Chapter 6. And that is because impulse is force times delta t. And so if you want the impulse to be small, you can either make the force small or you can make delta t very small. So in a collision or an explosion, the time of forces is very small. That delta t is small. So usually the impulse on a system is pretty small. So that's why here's this delta t thing. So if you're in a collision and you're a passenger, how does the airbag protect the passenger? It's sort of one of these physics principles should stand out to you as being better than the others, knowing what you know about Chapter 6 stuff. So if you do see it, definitely turn to your neighbor and share. Just make sure you and your neighbor agree. And I'll give you a minute to... Okay, so 95% of you who responded on time responded it lengthens the stopping time interval for the passenger, and so decreases the force exerted during the collision. So the idea being there is that the impulse is the thing, the delta p here is actually what's fixed, because you have some initial speed, whatever it is. It's whatever speed your car happens to be. It doesn't depend on the airbag, right? And then the car crashes, so it stops. So V initial and V final, neither of those depend on the airbag. If you have airbag or not, you're going to stop. But then for the passenger inside, the question is, over what time interval do you go from V initial to V final? And if you lengthen that time interval, you can decrease the force required to do that with the same impulse. Okay. Excellent. You guys are on top of this. This morning, an object of A of unknown mass is moving to the east, so you can kind of we're going to do sort of an example of that. And then this is A. And then B is moving south, B, like that. And so when they collide, if they stick together, which often happens, then they're kind of going this way. Because there's a negative... I guess if you were to define y and x like that, then there's a negative y component of the momentum coming from B. That's going to be conserved in a collision. And there's a positive x component of the momentum coming from A. And so the final momentum will be somewhere on that diagonal. This one confused some students, so you've got a collision. The idea here is that external forces are negligible. I guess, when multiplied by delta t, which is small. So there are a few very important forces. There's gravity, I guess, but that's usually down. Another very important force during a collision is going to be the friction from the ground on these cars. However, we say that during the collision itself, you can kind of neglect that large force because when you times it by delta t to get the impulse from that force is pretty small during the collision. So what that means is that the delta p for the system, which is a vector, should be equal to 0. And what that means is that delta p for the car has to equal negative delta p for the truck. So that when you add them up, you get 0. The system being the car plus the truck. Is that, you follow my reasoning there? Now what will happen in reality if the masses are different is that the velocity of the car will change a lot, and the velocity of the car, or the truck, won't change as much. Because velocity is the momentum divided by the mass. Okay, all right, good. It was a good question there. And then the idea is that the momentum of the car-truck system is constant, so delta p of the system is 0, but each object in that collision has a big change in momentum. And that was 100%, so I think we're good there. Some birthdays coming through. Athena, Wesley Chen, who also wished someone else a happy birthday, who was actually a student from last year, actually. Who's Gia? Lagan Singh had this joke. People are begging me to stop making jokes about momentum, but I can't stop. Appreciate that one. Sometimes I laugh when I open these surveys. Okay. Are we required to draw bar charts for impulse and momentum in the simplifying diagram step of equation? A question. So generally, I'm not too strict about following the exact same problem-solving style as your textbook does. But on the other hand, if you're kind of new to physics, I would say it's a good habit to try to follow that style if it helps you kind of organize your thoughts. And also, I think doing things like this, it may seem like it's consuming your time, but the other thing it's doing is calming you down and giving you something to do. And the last thing you want during a term test is to start feel panicked. Okay? And if you just rush through all the questions in 20 minutes in a complete panic, it's not as good as methodically going through, drawing your sketch and translate, doing your simplifying diagram, going through these steps that you know have been working on your homework and are going to work just as well when you're in a test environment. Which feels different than doing homework, doesn't it? But you got to try to make those two situations feel as similar as possible so that when you're succeeding on homework, you go in, succeed on the exact same kinds of things when you see the test problems. Forward force on a rocket is caused by expelling mass backwards. What's the difference between this and the force that causes cars to accelerate when their tires interact with the road? So this is actually a pretty confusing part of Chapter 6, is that you say momentum's conserved, but then it never really is. And the reason is because there's this almost infinite momentum sink coming from the Earth. So the Earth has a mass of whatever, 10 to the 24 kilograms, so it pushes forward on your car with some static friction that accelerates your car. Well, if you conserve momentum there, you would say that, I guess, the Earth picks up the exact same amount of momentum in the opposite direction. But you never observe that because it all gets absorbed when you divide by the mass of the Earth. You get the recoil velocity of the Earth is 0. And so it just seems as if some momentum is coming out of nowhere on the car. So what you do is you say momentum for the car is not conserved. It's just got an external force from the Earth called static friction, which accelerates it. That's different than a rocket where you have some finite mass of fuel going out one side, and then you can really check that momentum is conserved because the fuel picks up momentum in one direction and the rocket picks up equal and opposite momentum. These are great questions. Okay, so I'm going to do a lot of examples today. So I hope you're okay with that. That's the plan, because we're finishing up the chapter. This is this idea about constructing a qualitative impulse momentum chart, bar chart. Often the J term turns out to be 0 because you've got colliding objects where the external impulse is 0. But here is a cart that's going to the right with some large momentum, collides with a cart that's going to the left with some small momentum. So if you count 1, 2, 3 minus 1, I guess the total momentum should add up to +2. So finally, they're both going to the right. And they're stuck together, so they have the same size bar charts on the right. So what you're trying to demonstrate with these charts is sort of like the same amount of area over 0 on the left equals the same amount of area over 0 on the right. 2 and 2. But the main thing really is to solve these equations. Right? Once you've drawn it, you have to put it into actual symbolic form to really solve out the answer. And again, I'll give some examples of that. So you can sketch the process, choose your initial, final states, draw the bar charts if you want. If there's an external force, you can draw a J on the left-hand side. That adds to the initial to give the final. And then underneath the bar chart, you can put the equation and solve it out. I'll try to give an example of it, but length of the bars are supposed to be sort of qualitative indicators of how much momentum is in each thing. That J thing, again, represents the external impulse. And the idea is that you've got an equal sign in there, and the sum of all the heights on the left plus the height of the J should equal the sum of the heights of the bars on the right. Conservation of bar heights. Okay, let's do an example. A 0.020 kilogram bullet traveling at a speed of 300 meters per second embeds itself in a wooden block. So what I'm going to do, first I'm going to sketch before the collision. And then I'm going to sketch kind of just after the collision. The collision will be the bullet kind of embedding itself. So you've got this little bullet, MB, going along at some VB initial is 300 meters per second. And then over here, you've got the wooden block. Block starts with B as well, so let's use W. So VW initial equals 0. And you've got some mass of the wooden block. And then just after the collision, the bullet is stuck inside. So this is a collision in which they stick together, so their final velocity is the same. So I just draw it as one thing, is stuck inside the wooden block, and they're moving together. So you got a wooden block with a bullet inside. And you say that the mass of that system is the sum. Easy to find. And what you want to find is what is the, final. Not 0. Question mark. You need that. Okay. So, and then it says the block slides horizontally 4 meters on a surface before stopping. Determine the coefficient of kinetic friction between the block and the surface. So this is like the third step in the motion, which is the sliding motion. So what happens here is that the final velocity of the from step 2 becomes the initial velocity for step 3. Kind of doing this trick of splitting things into segments. So motion segments. So I'm going to draw it like this. And now the initial, maybe we could call this, instead of F, call it 2. VBW2 is the initial, going that way. The acceleration So I guess the force of kinetic friction is going to be mu sub k times n. We know that n and mg are in opposite directions, so we need to find mu sub k. I think that's the whole point here, right? And then it's going to stop. The final for this motion is going to be v bullet and wood 3 is equal to 0. And the acceleration here is going to be negative f sub k divided by the mass of the bullet in the wood. So in the simplify and diagram step, we can do momentum bar charts for the collision, I guess, which would look something like the P from the bullet plus the P, this is initial, from the wood initial, plus the J is equal to the P of the bullet in the wood final. And the way that looks is you've got this momentum bar chart plus 0 equals this. So and this should be the same height. So basically you've got the mass of the bullet times the V of the bullet initial plus 0 equals the mass of the bullet and the wood times the P, oh sorry, wrong, V. V bullet wood 2. So V, the bullet in the wood, is equal to the mass, and this is 2, by the way, mass of the bullet divided by the mass of the bullet plus the wood times the V of the bullet initial. So now, let's turn the page. This is 2, I guess. So you can plug it in. 0.020 divided by 1.020 times 300 equals 5.882 meters per second. And so what's known here is V bullet wood 2, and then V bullet wood 3 equals 0. We need a sub x. So what we're going to use is V bullet wood 3 squared equals V bullet wood 2 squared plus 2 times AX times X. So this is now it's a kinematics equation for the sliding motion. And I know the final velocity, I know the initial velocity. I care about the acceleration, I don't actually know it, but I do know the distance. I think it slid 4 meters, if you look back at the question. So the thing that I don't care about in this case is the time. So that's the equation we'll use. Solve it out for A. You get A sub x is equal to negative VBW2 squared divided by 2x. So you get negative 5.882 squared divided by 2 times 4 meters. And you get A sub x is equal to negative 4.325 meters per second squared. I like to keep lots of numbers on my calculator when I'm doing intermediate steps so I don't create rounding error or something. Now we use Newton's second law. You get A sub x is equal to negative F sub k, sliding friction divided by m. It's going to be negative mg times mu sub k divided by m. The m's cancel. That's lucky. But we had it anyways, but one less thing, I guess. So mu sub k is equal to negative a sub x divided by g. So you get negative of negative 4.325 divided by 9.8. And you get mu sub k, the negatives cancel, you get 0.44. And I'll just note that it's good that this is between 0 and 1. And that's because whenever I look at a table of coefficients of friction, they always tend to be between 0 and 1. So this gives me a little bit of extra confidence that if I got 50 or something like that, I'd be looking for a mistake. How are we doing for time? We're doing great. So, want to do another example? Kind of post these, but I always tell students there's a big difference between watching someone do a physics problem and doing it yourself. So it's important to do your homework, but I just want to show you how I kind of work through these things so you can see my reasoning. Okay, let's do an example, again, of setting up these bar charts. A little more qualitative. So this is the generalized impulse momentum theorem. Initial momentum, which is a vector, plus j, the impulse is a vector, equals the final momentum, which is a vector. And these are going to be the sums of the momenta of all the parts of the system. The example is as part of a safety investigation, two 1,400 kilogram cars traveling at 20 meters per second are crashed into different barriers. Find the average forces exerted on A, the car that hits a line of water barrels and takes 1.5 seconds to stop, and B, the same mass car that hits a concrete barrier and takes 0.1 seconds to stop. So this is a little bit like the airbag thing. So the idea is that there's initial, which is you've got some car, which is mass is 1,400 kilograms, which is going some speed, v, initial. I can set plus x's in the right direction here. And there's some barrier. And then final is that it stops. V final is equal to 0. Okay, that's the barrier. And so define here the system is the car, and then you'll have an external impulse coming from the barrier. So delta t is different. That's what matters here. So we really need to use that F times delta t equation for J for the different style of barriers. So the barrier here is external. So we're not going to have J 0. So I can do like this. Here's my system. And I've got an external force from the barrier. So what I say is that the P initial in the x direction plus the J in the x direction equals the P final. And the way that the momentum bar charts will look is something like this. So you've got a negative impulse. Does that make sense? Negative x impulse. So you'd say that m times v initial in the x direction minus f times delta t is equal to 0. Solve for f. And you get that f is equal to m times v initial in the x direction divided by delta t. And so A is going to be f is equal to 1,400 times, they're both going to have masses of 1,400 and initial speeds of 20. You divide by 1.5, you get 19,000 newtons. Seems pretty big. But when you divide by 0.1, you get something even bigger. 280,000. So there's a greater force from the concrete. Which sort of makes sense. So I've been in the lab setting things up this week for next week, actually. It's this stuff. So again, the stuff you do in practicals seems to become a week after we talk about it in class, which is sort of by design. I think it's good to kind of get exposed to it first and then try it yourself. So next week, you're going to have a cart and collide it into a stationary bumper, which is attached to the track. And you're going to have two simultaneous measurements going. You're going to both have the motion sensor going click, 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 click to see the velocity before and after. And you're going to have a motion sensor mounted to the, a force sensor mounted to the cart to measure that external impulse from the stationary clamp versus time. And so you'll have 0, 0, 0, 0 force, and then during the collision you'll have this big, big, big force. And you have a certain velocity that suddenly changes during the collision. And what you can do, the experiment here, is to roll the cart, let it go, let it collide while you've got all your data taking happening, and then analyze the data and try to compare the change in momentum to the impulse, both of which are things you can measure. We could do an example calculation, kind of related. So since we're sort of on this thinking about it. Let's say you've got a 0.5 kilogram cart on a low friction track. It starts, and you can measure from the motion sensor that it's going click, 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 away from the motion sensor at plus 1.2 meters per second, or 120 centimeters per second. It collides with the bumper, and you can see this force, which is negative, I guess, because it's in the negative x direction. It's going to slow it down, stop it, reverse its momentum. So you can, I guess, find the area. Let's say you found the area is negative 1.1 newtons times seconds. So remember, you've got a graph of newtons on the vertical axis, seconds of time on the horizontal axis, because it's the force versus time. So if you do the area, you get newtons times seconds, which turns out to be the unit of momentum as well. So what do you expect to be the final velocity of the cart? Let's do this as an example as well. There it is. So what I would say is initially, you've got a cart going this way. M of the cart is equal to 0.5 kilograms. Let's write down our knowns. V initial in the x direction. So I'm going to define plus x is to the right, is equal to plus 1.2 meters per second. Define the system as the cart. So the clamp on the end that you're crashing into will provide an external impulse. Same as that car thing. Define the system to be cart. Okay, so find the final VFX, this question mark. We need that. And we also know that J sub x is equal to negative 1.1 newtons times seconds. So that if you want to draw it in terms of, it's the same sort of thing. P initial in the x direction plus J in the x direction equals, well, actually, I didn't really draw that all that well. P final in the x direction. So I think what I should have done, let's cross the, cross that out. I think this should be a little longer. You got a big impulse that's not only stopping it, it's also reversing. So, but let's just put it into math terms. Mass of cart, V initial x, plus J sub x equals mass of the cart times V final x. You're trying to find the final. V final x is equal to V initial x plus J divided by the mass of the cart. So V final x is equal to 1.2 minus 1.1 divided by 0.5, and I get V final x is equal to negative 1.0 meters per second. So it starts with 1.2 meters per second just before the collision. Just after the collision, it's going backwards with 1.0 meters per second. And when I was testing this out, I tended to find this, is that the speed of the cart just before and just after the collision usually reduced a little bit. I guess I must have lost some energy or something in the collision. All right, so I want to do the rubber ball thing. So it goes down, bounces up again. So let's do a top hat question for you guys. Let's say we've got a very bouncy rubber ball that when dropped from a certain height hits the floor with some downward speed. Since it's so elastic, it bounces back with approximately the same speed as going upward. It's one of these little super balls hitting a concrete floor or something. I don't have that. But so which of the statements about the bounce are correct? A, the ball had approximately the same momentum just before and after the bounce. B, the magnitude of the ball's momentum was approximately the same just before and after the bounce. C, the ball's momentum was conserved during the bounce. Or D, none of these are correct. I'll give you a chance to think, pair, share. Think about it, and then pair up, find a neighbor. So yeah, that's the idea. The magnitude is the same. So the momentum changes quite a lot. So I'll just circle that. I like B. So let's actually look at these different kinds of collisions. Can we try it with the? You wanna? I'll let Jonathan hit aux plate. Thank you. Good, that's the video. So what I have is two balls, which are black, which are going to bounce off a black table, so that's fun. Let's see if this works. Whoop! So I don't know if you could see that. Can you? If I sit, is that okay? So one of them is a regular ball, and one of them is this funny sort of, it's called the happy and the sad balls. So, so let's talk about that. Work okay? We need orange ones. Like this. These are two objects which are striking a flat table top. This is what I call the happy and sad. Scenario 2, for some reason, it stops. And so the idea here is that they both change their momentum, because momentum is a vector. Certainly, with scenario 2, it stops, and so all that original momentum goes to 0. But then, in scenario 1, it changes it twice as much. So the impulse on the happy ball is twice as much as the impulse on the sad ball. We talked about this last time as well. In Chapter 7, we learn more about elastic versus inelastic collisions. So the difference is something to do with how the internal energy gets stored in these different balls. In an elastic collision, internal energy doesn't change much. It gets stored elastically and then gets immediately re-released. But in an inelastic collision, there's some sort of heat generated or internal energy, like damage or something like that, which absorbs that energy and doesn't give it back right away. So it allows its speed to go to 0, and therefore the impulse is a little less. Another top hat. Well, it says as shown, but I forgot to put the image on the top hat, so you'll have to look at the screen for the image. As shown, two people sit at opposite ends of the boat that is initially at rest. Hopefully I'll add this before the video folks do this question. The person to the right throws the ball to the person on the left. So, what I'm going to ask you about is the velocity of everybody else, the boat and the people, just after it's thrown, so the ball is in midair, and then when the other person catches it, after it's been caught. So, you imagine it? You throw the ball, the other person catches it. So first the ball is at rest, then it's thrown and flying, and then at the end, the ball is at rest. So one of these should look good to you. I'll give you a minute to think, pair, share. I'm not going to show the timer because it's good to have this picture. So you got 10 seconds to click this in, please. Choose an answer, and then I'll discuss. Going once, going twice. Survey says yeah. So I like it. So the idea is that while the ball is in flight, the ball is moving to the left. And so to conserve momentum in this system of being the ball plus everybody else, then the total momentum was 0 before it was thrown. So during the throw, it should still also be 0, so everyone else moves to the right. So that's good. And then when it's caught, again, momentum goes to 0. And so everything stops again. So I liked A. So this is kind of, again, we're going over this again and again, but it's sort of a way of propelling. So cars change their velocity because of an interaction with the road, which is definitely an external force. And maybe a ship in the water pushes water backward. So a rocket in empty space has nothing to push against, but if the rocket and fuel are at rest before it fires its engines, after the rocket fires its engines, the momentum of the system of the ejected exhaust plus the rocket should still be 0. So if the exhaust comes out fast enough in one direction, you can imagine the rocket going the other way. So I got a balloon, and it's filled with air. Its momentum is 0, so the momentum of all the air in the balloon is plus the balloon, which is, I guess, the rubber part of the balloon, is all 0. So if I let go of this balloon, all the air is going to shoot out one direction. So what do you think is going to happen to the rubber balloon? You've probably done this, right? So it's probably going to shoot off. So that's exactly the same sort of thing. You've got a propulsion that's happening from some ejected material called thrust. Thrust is the force exerted on the fuel by a rocket during the jet propulsion, maybe 1,000,000 newtons or something like that. That ejects the exhaust up to Mach 10, and then the thrust provides the impulse that's necessary to change the actual momentum of the rocket part itself. Okay, and same's going on with the balloon. When you open the valve and release it, I guess also if you were to stand on a skateboard and you're holding a medicine ball, if you were to throw it that way, you'd probably actually be able to propel yourself in the opposite direction. There's some analysis. So you've got initial momentum is 0. This is the way you could look at it, is everything on the left-hand side equals 0, but then the momentum of the rocket is positive and the momentum of the fuel is negative. So if the rocket's already moving, more fuel expulsion will speed it up even more. So the way it looks like for this is that you've got some initial velocity of the rocket, and then you've got the final velocity of the rocket plus the final velocity of the fuel. You can solve this out to get the change in velocity of the rocket and divide both sides by delta t to get the acceleration of the rocket. So just looking at that again, in this equation, negative mf is delta m, the change in mass of the rocket when the fuel leaves as exhaust. So this gives us an equation for the acceleration of a rocket in deep space. This is what's called the rocket equation. It was in the pre-class notes as well as it's going to be in the post-class notes. The acceleration of a rocket is determined by how much fuel, the delta M, how much fuel it leaves the system divided by how long it takes that to leave the system, times the speed of the exhaust relative to the rocket divided by the mass of the rocket. I'll give an example of doing that if I have time. Yeah, I think I do. Let's use that equation. So a rocket is fired in deep space where gravity is negligible. In the first second, it ejects 1/160th of its mass as exhaust. So this is the mass of the rocket. It's accelerating to the right with A sub rocket. A sub rocket is given is 15.2 meters per second squared. And you've got this V of the fuel or something like that is actually what you're trying to find. And you also have the fact that in delta T equals 1 second, the delta M divided by the mass of the rocket is equal to 1 over 160. So that's the known information, which I like to put in my sketch and translate. And then the idea here is that since it's in deep space, momentum is conserved because there's no external forces. So there's no external J or impulse. So we're going to use the rocket equation, which I just derived on the previous slide, which is that A sub R is equal to the V of the exhausted gas divided by M sub R times delta M divided by delta T. We're just going to solve for V of the gas. V gas is equal to A sub R times M sub R over delta M times delta T. It's 15.2 times 160 over 1 times 1 second. So you get V gas, 2,400 meters per second, something like that. Okay. Should we try these pucks? We had a whole plan. So this one is going to be easier to see from the balconies, actually, I think, than from you guys. I don't know if you're going to be able to see it. But maybe you want to send it this way. So Jonathan's going to send the puck one way, and I'll send the puck in a perpendicular direction. We'll try to get them to collide. See if we can not miss here. You go first, and then I'll try to hit you. Oh, no. Oh, I did. Okay, good. And they're also rotating. Idea being that Jonathan gave it some one direction, I gave it another, and then they went off on a diagonal, if you were to see it from above. So I have a whole big, huge, long example of a traffic collision, which, seeing as it's Friday, I don't think I'm going to actually do, and plus it's like very close to noon. But the idea is that you've got a Hummer, yellow Hummer, which just, doesn't that already annoy you? Okay, collides with a blue Toyota, and one's going south, one's going east. The speed limit is 50 kilometers per hour. After the collision, the two cars stick together, and there's this big screech mark on the ground, which is 10 meters long, angled at 32 degrees east of south. So you're like the cop who arrives at the scene half an hour later and measures the length and angle of this big, long, screeching skid mark. And then the question is, how fast were the two cars going before the collision? You can actually solve that with that information given. But like I say, I think that's going to be something we'll do on Monday to finish off Chapter 7 or Chapter 6. Then we'll start on Chapter 7. And the question to ponder, a woman carries a bag, a horizontal displacement of d, During this time, she exerts a constant upward force on the bag F. What is the work done on the bag as she carries it? So I'll see you Monday.